Hello and welcome to this video on first order differentials. Now this is not the first order differentials that you'll probably look at in your normal maths, where literally all you have to do is rearrange terms in x's and y's to get the y's over on the dy's and the x's on the dx side, integrate both and Bob's your uncle. No, this is more the further math style of differentiation, or further math style of differentials, which is difficult and easier in its own special ways. Anyway, let's get on with the question. Now then, my question today is by using an integrating factor. Now, integrating factors are wonderful things, which I will go and explain what they mean very shortly. dy dx plus tan x y is equal to tan cubed x sec x, given that, and the given that is important. Now this is actually one lifted from the Further Pure 3 paper 2015 for AQA, if you would like to have a look at the question in a bit more detail, but I quite like this one because it goes through a number of really cool kind of jiggly things. Now then, any first order, before you start doing anything, you want to make sure that every first order differential that you ever look at is going to be in the form dy dx plus p to the p to the y is equal to q to the x effectively. What this means is that there is no value before the dy dx. That's really important. You want to divide so that you have got rid, so basically there's nothing before the dy dx, and anything else, even if you have to divide, you know, so that whatever your value of p is over a trigonometric function and the q value looks awful, it doesn't matter. You need to make sure there is nothing before the dy dx. It can only be a singular dy dx. That's really important, and it obviously has to be in the form dy dx plus something to the y. Now we've got that sorted. Now the other thing is use integrating factors, which is the integrating factor is e to the integral of whatever your p value is, which is the number before your y, dx. That's important. Basically, if you screw that up, you will never be able to finish the question. So make sure you know those two formulas like the back of your hand. If need be, write them in the exam. It makes your life a damn sight easier. Right, moving the paper forward. We have, in this case, we know that our value of p is tan x. So I is equal to e to the integral of tan x dx. So therefore we can integrate tan x, which is e to the ln of sec x. Ooh, how convenient. What happens if we have an e to the ln? They cancel, which means all we have now is I is equal to sec x. That's really convenient, actually. Now then, the easy way of checking whether you've got your integrating factor correct is literally to times every value in the original question by sec x. Trust me, this does make a hell of a difference, and it's quite important that you do that. So, and it's a really, really good check. So that would be sec x dy dx plus tan x sec x y equals tan cubed x sec squared x dx. No, sorry, just tan cubed x sec squared x. Now the reason why this is important is because we look at our original question. If we differentiated tan, we'd get we look at this one, if we differentiated sec, then we get to tan x sec x. We differentiate y, we get to dy dx. So as you can see, on both of these there is one bit that is the differential, there's one bit that's differentiated. As they match, we know that we're on the right lines. Now then, we need to actually work out how we're going to integrate this, which is kind of a useful feature. So we can do d dx of sec xy, because that's the original and also that's the original, so sec xy is equal to tan cubed x sec squared x. Now obviously integrating that is dead simple because you're effectively just going to remove a ddx, which means that it's just going to be sec xy. Well, sec x in brackets then y. That one on the other hand is a bit more of a troublesome thing. So we have a technique for this. Now some of you will remember in your proper A levels something called integration by substitution. This is going to come in very handy right now. If I write you the integral, if I say tan cubed x sec squared x, where, of course dx, where u is equal to tan x. So that will go to u cubed sec squared x, u equals tan x, du dx is equal to sec squared x. So therefore dx will be equal to 1 over sec squared du. So therefore what we have is u cubed sec squared x times 1 over sec squared x du, which is, to be honest, quite useful because, as we can see, the sec squareds cancel, which just gives us an integral of u cubed du, which obviously those of you who've done basic integration will know that that goes to u to the 4 over 4, and obviously because we haven't put limits on, it will be tan to the 4 x over 4. This is very important because it means that now we can properly integrate that function, which means that all we have is sec xy equals tan to the 4x over 4 plus c. Now then, that will get us probably about 7 out of 10 marks, 7 out of 9 marks. The important bit of this is actually this bit, given that y equals 2 when x is pi over 3. This is really quite important because it actually tells you, what your c is going to be, because you can't forget about c when you're integrating. So obviously subbing those in will give us sec pi over 3 2 equals tan pi over 3. So let's see, tan to the 4 over pi over 3 over 4 plus c, which means that which plugging those in gives us 4 plus, or should I say 4 equals 2 1/4 plus c. c is equal to 7 over 4, which means we can finish this question as sec x y is equal to tan to the 4 x plus 7 over 4, and just to be quite nice and rearrange, we can do an inverse sec and do y is equal to sec to the minus 1 tan to the 4x plus 7 over 4. Now depending on the question will depend on whether you actually need to get it in terms of y equals. Normally it will state, but in a case like that one all you have to do is write sec to the minus 1. I tend to do it just because it's a bit easier. But yeah, there you go. First order differentials in a nutshell. Honestly, it pretty much doesn't get a lot worse than that because all you've got to do is bang out your method repeatedly until it works. Anyway, thank you very much. See you next time.